Recording.
Oh, yep, somebody's got it.
It's
Yeah.
transcript.
Whoever's recording, thank you very much. If you could then
Yes.
pass it back and we can share it with anyone who actually couldn't turn up.
Sure.
All right, so we'll make a start. Nice to meet you all sort of in person. I'm Ian Murray. I'm Deputy Head of School for Electrical Engineering, Computing and Mathematical Sciences, which includes physics. So nice short name to remember. And I'll be taking you through the lecture today. I'll also introduce Savash Kaksar, who's will be taking you through the lab. So off you go, Savash, just who you are.
Hi, makes it easy. I'm the same school as Ian. Work with embedded systems, sensors, IoT, and I'll be going over a practical hands-on exercise with you. So looking forward to answering your questions and talking to you about the things part of IoT today.
Okay, thanks. So a couple of housekeeping things. Well, they're not really housekeeping, but we'd like to run this as a discussion as much as we can. Nobody really enjoys talking at other people or just being talked at. So please feel free to jump in, type some questions in, raise your hand using the hand icon, which I think, yes, it is still there in Teams. And one of us will jump in and let you have your say. So please don't be shy. Interested to hear what you have to say. The other thing is this is the first time running for Optus, so we aren't 100% certain on what level to aim things at. So if we're going in too much detail, please let us know. If we're not going into enough detail, also let us know. We really want to make this suit what you guys are after and what sort of level you're at. The idea behind the masterclasses is to very much go into a bit of depth that's not really in that curtain credential. They're very introductory, fairly low level courses aimed at just introducing topics to people. So here we will try to delve in to enough detail so that you can communicate well with subject experts. So if you're all dealing with the design engineers or the software developers, we really want you to be able to talk to them at their level, but perhaps not be in a position to do the design work yourself. So today, we're going to have a look at IoT things. We'll have a look at some of the terminology. There's a little bit of maths, but it's certainly not serious maths, but it is something that's really, really important to know. We'll be looking at some components and sensors and actuators, and I'll have a brief talk on how we go about developing prototype systems as well. So to begin with, back to school. What is electronics? Well, electronics is the study of electricity and physical components and circuits that make up the electronics. We need to have some standard definitions to understand this. We've all seen pictures of atoms before. We've got electrons, which are the negatively charged object which orbits around the nucleus of the atom, and we have positive charges in there and neutral charges with the protons and neutrons. The way semiconductors work, we're not going to go into. The way things conduct, we're not going to go into. It's really enough to say that for any electrical circuit, we need to have a closed circuit, and I'll explain what that means in a second. And it is the movement of electrons, either vibrating or moving, however you want to look at it, through this closed circuit that is our current. And I'll explain further as we go along with that as well. We have some standard things that we use. We have electrical current and voltage and power. Now, these are three aspects of the same thing, if you like. And if we use the water analogy, we consider that the current is the volume of water that's moving through a pipe. So the amount of current in amps that you have pushing down a pipe is the volume of the water, how much energy you're actually transferring. The voltage is the pressure behind that. So the higher the voltage, the more current you can get through. And power is a little bit different. It's the water that's consumed in the operation. So whenever we have electricity going through a conductor with resistance, the energy is converted normally into heat, which means we have a power loss. We won't actually go too much into power in this, but we will look at the relationship of voltage and current, because that's really, really important when we start to look at how we measure things and how we get an input to our microcontrollers in an IoT system. So we're only going to deal with a little bit of DC, nothing terribly difficult, nothing terribly hard. And this is the maximum amount of mass we're going to cover, really, sort of. The fundamental theory we use, or formula we use in electronics, is Ohm's law. This is the relationship between voltage, and remember I said that was like pressure, current, which is our quantity, and resistance, which you can think of as the diameter of the water pipe, or the restriction you place within a circuit to limit the amount of current. So the relationship is, the higher the voltage, the more pressure we have, the greater the current and the lower the resistance has to be. Or if we move that around, if we have a low resistance, we would have a very high current. So these three formulas are the way we calculate what voltages and currents move within a circuit, and how we calculate the resistance to limit the current given a certain voltage, so that we don't let out all the magic smoke that's inside electronic components and makes them work. You'd be surprised at how quickly they stop working when you let that smoke out. So Ohm's law states that voltage is directly proportional to the strength, which is the current, multiplied by the resistance. And as I said, if you think of this along the water pipeline, it sort of makes a bit more circuit. Now, for anything to happen within an electronic circuit, it needs to be a closed conductive path. That's what I meant by a closed circuit. There must be a way, if you want to think of it like this, for the water to go from the positive end of the battery, the water source, all the way around the circuit and back to the sink, or the negative end of the circuit. If there is not a path where the electron flow can happen, then we don't have a closed circuit, therefore we get nothing happening. Circuit also needs an electrical energy source, such as a battery, to start off the flow of electricity. So if we don't have an energy source, nothing is going to happen. Fairly obvious, but something we need to keep in mind. All right, so looking at our initial circuit, this is a very simple circuit that's going to turn our LED on. And what we have, hopefully you can see my pointer, Sebash? Nod, I can still see you.
Yep.
Okay, so what we have here is a resistor, and this squiggly line is a schematic image for a resistor. We have a battery, and this is our schematic for a battery with a negative and positive. One thing to bear in mind with all of these, some components have a polarity, so you need to make sure you put them in the right way around. And I think when you're doing up the circuit in Tinkercad, Sebash, pop the diode, the LED in the wrong way around, and just show what happens when you get it wrong. Okay, and this particular object is a light emitting diode, and we can tell that because it's got these arrows pointing out saying it's going to emit light. In this one, we can see that we have a circuit, right? Because the current can flow up here through the resistor, through the LED, and I'm just through the LED, and then up back through to the negative side of the battery, which we could think of like a sink. If we had a break anywhere here, or the resistor was missing, it's not a closed circuit, therefore we'll get no current flow. We have a resistor in here because if we apply 6 volts directly to an LED, it'll burn out. So we need to limit the resistance, limit the current via this resistor to what power level or what current that LED can cope with. So in most cases, an LED sits around 20 milliamps or 20 thousandths of an amp to 60 thousandths of an amp for normal operation. So going back to our Ohm's law, we can work out if we want this to equal 0.020 of an amp, and we have our 6 volts, we can then work out what our resistance is from that one. Okay, and this is one of the reasons why Ohm's law is so terribly, terribly important in any of our electronics. This is showing the polarity of the LED, by the way. You can see the triangle is pointing in one direction. That means that side is positive and that side is negative. That's an anode and that's a cathode. Okay, we'll come back to a little bit on the Ohm's law, particularly about switches and how we read switches in, but we'll need to know a little bit more about some of the components that we're using. There's 2 types of component, generally. we have active components and passive components. These can be either linear or non-linear. Linear means that their attributes change in a straight line format. Non-linear means that they can vary with other attributes. So a non-linear device might change its resistance, for example, according to heat. So if it gets hotter, it becomes a lower resistance, and that's how we get things like thermal runaway. But they have a non-linear response to heat. All passive components require that external power source for current to flow, and they don't do anything directly on that circuit. They will either limit the current, they will store energy, they will oppose changes in voltage, and do things along those lines. Whereas active ones can be controlled. If we look at a transistor, that can be used as a switch, and we've got an example of that coming up shortly. So the fact that we apply a voltage to an active device and it does something is what makes it that active device. With a passive device, it just sits there and we don't interact with it, we don't do anything to it. So examples of passive, there's a resistor there. We're using the light dependent resistor in the exercise today, are we? Yep, so we'll have a look at a light dependent resistor, and that's something that reacts to light, and the resistance changes depending on the ambient light. Capacitors store energy. Inductors oppose change in voltage. Switches, of course, they're passive, they're either on, off, and transformers are another passive one. Active, lots of things. We'll have a look at a few of those. LEDs, diodes, which limit the current flow in one direction only. Again, going a little bit out of what we need to cover here. And other components like integrated circuits. Going back again to high school, we should all hopefully remember what direct current and alternating current is. This is important for us as well, because we can't really use alternating current. We need to turn it into direct current to make any real use of it. DC has the current flow in one direction only, and alternating current has current flow in both directions. Our mains is alternating current, our batteries DC. Be very careful of DC. It's very dangerous, and low voltages can cause a lot of pain and death because the current flow is only in one way. And what it does is it cramps the muscles. So instead of getting a fluctuation of 50 times a second that you get with AC, with DC, it just cramps and stops. So you'll find that if you get a decent whack of DC, usually around 50 volts, your heart just stops. So rather nasty, whereas AC just hurts. I've been hit by it often enough, I should know. Okay, your normal electricity generation generates AC current. That's simply because if we've got a moving device like a turbine or a motor, it's easier to produce alternating current, whereas chemical devices such as batteries, solar cells, tend to produce DC only. And of course, we need to convert from that. Okay, now we've all seen things like a digital circuit and analog circuit. What is the difference? Well, a digital's really simple. It's either on or it's off. It's digital because there are only two states, on or off, 1 or 0. We've got an example signal here. We've got ons and offs representing things. And here is our analog signal. Analog varies infinitely over time. So that means it can be any particular value down to as many decimal points as you like to measure. It changes in a fairly fluid sort of way and has many, many disadvantages. The first one is it's very easy to see, is this a 1 or is this a 0? So if we get noise in there or corruption of the signal in any way, it's very, very easy to then turn it back into either a 1 or a 0 because it's only one or the other. Whereas with an analog, it's extremely difficult to determine exactly what the signal is doing and what it means. So those of us who are old enough and remember AM radio when they used to play music on it, that was an analog signal that was sent. And it was awful in the distortion. It was really poor quality audio that you got through. If you now compare that to CDs and digital radio, DAB radios, where we have crystal clear, no distortion, it's because we can convert ones and zeros back to their original form fairly easily when compared to a multivariate, highly variable signal level that we get with analog. Okay, so we'll move on. With the development of your prototypes, there's several stages we go through, and they are the design phase, where we look at the concept, research, the circuit design, and create the circuit diagram. Now, we looked at a very simple circuit diagram before with just a battery, an LED, and a resistor. That's a schematic. That is a representation of what the circuit looks like to engineers. Luckily, we don't have to work that way all the time. When Savash gets onto the Tinkercad exercise, you'll see we can do all of that by using what looks like real components. Tinkercad has the ability to convert that into a schematic. So if you get a chance, Savash, might be worth just quickly doing that as well. If not, doesn't matter. But we do go through several stages with this. The design phase is thinking about the ideas. This is where, in what I assume is your case at Optus, a client will come in and say, I have a problem, I want to be able to do this, how do I go about it? Your guys go off and do the research, they work out approaches to it, what components they would need, how they would go about solving the issue, and come back with a suggested design for the prototype. You then go into a prototype phase where you actually build something that is probably not anything like, or doesn't look anything like the a device you finally end up with. It can be made up of multiple boards, lots of bits of wire hanging off, but it's a proof of concept to see if the technology that you're using and the approaches you're using is capable of solving your customer's issue. Once you get through that and you've got the general idea worked out, you've got most of the bugs worked out, you can go to your production phase. And this is where you start to make up the printed circuit boards, such as those shown in this image here, which would be close to your finished device. Normally, you will prototype these again as well. You'll go through another debugging session to work out any design flaws that are there, particularly in environmental ones like heat dissipation or weatherproofing or creating the housings for it. And then you put it out to field testing and go to actual production. So looking at a simple circuit can be made by just connecting up the components on one of these. It's called a breadboard. And in Tinkercad, I hope everyone's had a shot at getting registered for that. You have a image of a breadboard, and it works in exactly the same way. And this is a great way for doing little home prototypes or quickly checking things out. We connect a power source, in this case a battery, but we can be using other power supplies. In simple circuits, we'll be using the Arduino IDE simulator that is within Tinkercad, but it's basically the same thing, and it's a very, very simple way of setting up some trials and prototyping things that you want to see if they work for your client. We will need to program a few things up, but the good news is there's several ways we can do it. The Arduino allows us to use a form of C, Pythonish, that is in their IDE. That's the integrated design environment. And we'll have a look at that. And we have that simulator sitting in Tinkercad as well. And you'll see how you write the program to do things. And a few keywords there, but we won't go into those because it's too much programming for the moment. So what we'd see in Tinkercad is something like this, which looks very much like our physical component. In this case, we've got a pulse width generator. Arduino is connected to the motor drive board, and we've wired it up. So you can see it physically looks something like a circuit that you would set up at home with real components, but this is all done in simulation. We can program it in Blocky, which is a nice graphical way of creating programs. And as we can see here, it's not really a programming language, and the blocks will only fit together in the right way because they've got little keys on them like a jigsaw puzzle, and they're very English-like. So if we look at this, set your wait time to 5, and it'll be in seconds. Then there's a comment, set your built-in LED to high, which means turn it on, set pin 10 to low, set pin 11 to low, and this is actually setting these pins down here to either 1 or 0. So Blocky is really, really simple, but it's not terribly efficient, but can do what we need it to do. Moving on to some of the sensors. Now, we didn't really cover too much in sensors on the curtain credential, but there is a multitude of sensors out there, and there's just a few sitting here in this diagram. But sensors are devices that can detect an event from a physical environment and respond with either an electrical or optical signal. Some of the sensors that we use are light detectors, pressure detectors, inertial measurement units, which is Savash's favourite thing. And he can talk about those forever, if you like. You've got them in your phone. So if you look in your phone and you are playing a game and it's controlled by the way you use your mobile phone and move it around, that's using the inertial measurement units within the telephone to read its position and its offset to interact with the game. And that's just a sensor. All of these sensors we use in IoT to work out what's happening in the environment that we want to measure. So if we're working in an agricultural environment, here we've got a little home watering kit that we built some time ago, and it has a moisture sensor on it. When the moisture reaches a certain level, or the dryness, it turns on a water pump, which pumps the water in there. When the moisture levels get back up to what we would like, it then turns the water pump off. This one also SMSs you to tell you it's watered the plant. You don't have to worry about it. So that's a fairly typical IoT device using a sensor. One thing I would point out, though, is when you're looking at sensors, don't look at just what they're designed to do, because in many cases you can use sensors for things they aren't designed to do. One of the ones we've done is using a impedance sensor, so it measures the resistance through certain materials to measure the resistance across the human body, which we can then relate back to hydration levels, because muscle and fat cells store different amounts of fluid, and we can actually calculate back from that what their hydration level is by measuring the resistance of the human body. If we want to measure the salt concentration in water, we don't actually measure the salt, we measure how conductive the water is, and that gives us a relative level of salt. So don't think in a linear manner. Sensors can measure many other things that they're not designed to do, and in many cases, we actually do implement that. Actuators are the other side of the story when we want to do something. So these can be linear or rotary activators. They can be mechanical switches, motors, all kinds of things, but they're just devices that we can have something acted on in our environment. Quite often used for opening and closing things, for turning on and off fluids, for moving, say, print heads on a 3D printer, and that sort of thing. So, okay, one of the things we'll be looking at next week along this design principle is Packet Tracer. Please go and register and download and have a shot at Packet Tracer. There's a really good short course available, which I've linked somewhere. That'll teach you how to install and just get started with it. It's a great tool now and in the future. If you ever want to start prototyping a few things to show your clients, to see if your network's going to work, to see how you can connect things. So a very worthwhile tool. It comes with an inbuilt microcontroller unit and single board computer, which are basically like an Arduino and a Raspberry Pi, if you're familiar with those. So you can actually do some fairly reasonable programming on them, and it has lots of actuators and sensors that you can put in. This is more of a simulator rather than a design tool, because it will simulate the environment, whereas Tinkercad will allow you to design and program an environment. So they're slightly different things. I'll also point out the difference between a microcontroller and a microcomputer here, or a single board computer. A microcontroller is, as the name suggests, it controls things. It's usually a small computer that doesn't have an operating system. It's programmed for one thing and one thing only. So it's, for example, you'll have a microcontroller in your rice cooker or your microwave oven. It's never reprogrammed. It might be updated for security reasons, but it never does any other task apart from the one it was initially programmed for. I think we've got a comment there, Savash.
Yes, so a quick question. I remember this from 2007 when I was a much more basic.
Oh, it was very basic in 2000s.
Yeah.
It's actually pretty advanced now. It's a really, really good tool. Okay, so a single board computer is basically like a mini laptop or some other computer that can be used for general purposes, quite often reprogrammed. things along those lines may be your programmable video recorder, your PVR, or your mobile phone, which is a device, but it has a single board type computer in it. But the lines are very blurred nowadays. It used to be very, very different back in the 90s, where it was very distinct what a microcomputer was and what a microcontroller was. But now it's very blurred lines because we've got operating systems running on MCUs with Linux and Android, those sort of operating systems. And we have dedicated single board computers that don't necessarily run an operating system. Okay, so we will be playing with Packet Tracer next week, actually, when Naz comes along and tells us how to use it. Okay, so that first bit was very general. This is what could be a little bit tricky, and we're going to talk a little bit more about what the signals mean and how we read them. So I'm hoping that this is of the right level for you guys. If it's too simple, please tell me. If it's too hard, please tell me. As I said, our first time running through with Optus. So there's some of the things we're going to be looking at. We'll look at the signals. We'll look at some equations for the electricity and how to calculate resistance. We'll talk about general purpose input-output, pulse width modulation, which is really handy in controlling motors, and analog to digital converters. They're really important because our world is analog, right? That continuously varying voltage level. The computer's world is digital. So we want to read our world, convert it into digital, so the computer can do something on it, then convert that digital stuff back out to an analog system so that we understand it. All right, so that's really a critical factor in the IoT and all electronics, actually. Right, so series and parallel circuits. The only thing we're going to touch on here is resistors, and we do this because we use them as voltage dividers and current limiters in all of our IoT. If we connect things in series, and we can see here, we go from the voltage through R1, then straight after we go through R2, we simply add the resistances up, and that will give our total resistance for the circuit. We use this because it can divide our voltage. So if we go back to that V equals IR, voltage equals current times resistance, we can work out what the voltage is across this resistor by knowing what the current is through the whole circuit, add up the two resistors, voltage divided by those two resistances gives us our current through the circuit, multiplying the current by one resistor tells us what voltage is dropped across here, which we can then measure off from this point. And we'll see that when we're doing voltage dividers and switches and other things where we use this series resistance to work out whether a switch is on and to read voltages in and out. In parallel, we don't use this very often, and particularly not today. The voltage comes from or is applied at one end, and there's three branches for the current to go through. So you can actually have 3 times the current running through as if there was one resistance because there's 3 branches. So the resistances work by this formula where it's a reciprocal of the addition of all the individual resistances. Again, don't worry about this one too much. This is the one we actually use. Okay, so the example coming up, here we go. We've got a nice series resistance with 3 resistors, a 10 ohm, a 50 ohm, and a 60 ohm. We can work out our overall current because we add the resistances up, 10 plus 50 plus 60. We divide the voltage by that overall resistance, and that gives us 0.25 milliamps. Right. So that's, don't want to go back. And that's important because if we take this 25 milliamps and we want to know what the voltage is between this point and this point across resistor 1, well, we just multiply the 25 milliamps by the 10 ohms and we get 0.25 volts, which means if we took a lead off here and keep doing that, if we took a lead off here and put it into our computer and read it, we could read 0.25 volts. And this is an important part when we're reading things. So if we considered replacing this resistor with, say, a light dependent resistor that varied with the amount of light, the level of the voltage we read off here is dependent on the resistance here, which is dependent on the light. So from that measurement, we can tell how bright the lights are within a room. And this is the reason it's important to understand the voltage drops across these very simple circuits. When we put a sensor in series like this, with another resistor further down the track, we can use the variance in the sensor resistance to work out what the value of the sensed item is, such as light. So here's an example here, working a voltage divider. This could be our variable sensor. We have a voltage divider. Our resistance is R1 plus R2 because they're in series. We work out our current, and we can get the voltage across the first resistor by multiplying the overall current with the value of resistor 1, and that will give us our voltage out here. So what happens if resistor 1 is 0 ohms resistance, in other words, a short circuit? What is our voltage out? That would make this a direct connection through here. So our voltage out would equal our V in up here. So if we're thinking along switches, bear that in mind. If R1 is infinite resistance, and means there's no connection between V in and this point, well, that means our V out is connected to the ground, which is 0 volts. So our V out would be 0. And this is how we read switches. Oops, that's transistors and switches. So if we replaced R1 with a switch, if it was open, that's when it's infinite, we would have 0 volts out. And we could put that into our microcomputer and say, if it's 0 volts, the switch is open. If V out is at the same level as V in, right, if that was a short circuit, the switch is closed, we would have our, call it 5 volts on the V out here. And our microcomputer can say, aha, that's 5 volts, therefore the switch is closed. And this is how we can read switches, really straightforward. Okay, we can use a transistor as a switch, and we use it the same way as that voltage divider. Here we have our control signal, so our microcomputer can tell it to turn on or off. If we apply a positive voltage here, that transistor turns on, which allows this to conduct electricity through, and the motor turns on. And it's basically like that. So this is how we control motors directly. Sorry, was that a question? Oh, okay. Yep. So this is how we control items from a microcontroller. The input and output, I won't go too much into this because this will be in the Arduino bit, but we've got different sorts of pins which we define as either input or output. Input pins are obviously for reading something into the microcontroller, and outputs are to control things externally. And they can act a bit like a battery, if you like. So we'll skip over this one a bit, I think, because we're using up a fair bit of time. Okay, and when we put this together and we have a switch on a microcontroller, here's our little switch. When it's open, there's no connection here, so pin 1 would read low or 0 volts because it's connected to the ground. If we close the switch, VDD is connected directly to pin 1, and pin 1 would then show as a high, the switch is closed. And we're going to go through how we do this in software a bit later on. That's done in just reading pins. Okay, one of the other things I wanted to cover is pulse width modulation. This is how we control the speed of motors, and we normally have a pulse width modulation pin on every microcontroller. The term you find here is the duty cycle, which means how long is the pin turned on. And it works by pulsing. So we can see here that if we've got a 0 duty cycle, there's no pulses. Therefore, you're not putting any power out to the motor. If we start to put little short pulses on, in this case 25%, then we will get a little bit of power coming out every now and again. And as we move through to a higher duty cycle, we can see we're applying 5 volts more often than we're not. So therefore, we're applying more power to the motor, so the motor will spin faster. And if you have a 100% duty cycle, you'll have the power on all of the time, so the motor will be spinning as fast as it possibly can. And this is really the way we control motors and things of that ilk. The only other thing to remember, and this becomes very common, is quite often in computer terminology, we don't deal with our sort of numbers. We deal with a representation or a scale of numbers. In this case, 0 does match 0%. If we have an 8-bit pulse width modulation pin, to get 100%, we actually set it to 255 because 8 bits can represent 256 different numbers, 0 to 255. This is common also in the A to D converters. So a 50% would be 128 because of that overall scale of 0 to 256. Quite often these can be in hardware or software implementation. We can use it for lighting and servo motors, many other things. So it's worth knowing what the pulse width modulation does and how it works, and the fact that it's a scalar representation, not a straight percentage normally when we work it. We'll see this again in our digital analog converters where we have a scalar, not a direct value. Signals and filtering. Now, this gets really, really complicated if we go into it, but we're not going to. We're going to just cover some bare basics of what it means. And a lot of this will already be familiar to you. So with analog signals and digital signals, we can only store digital signals as bits, right? So it has a single value. When we're doing our conversion from analog to digital, we store things as an array of numbers. And the parameters for this are the bits per sample and the sampling rate. So we think to our audio. We all know about our 16-bit audio that we get that has a 22,000 something or other sampling rate. And that's a fairly low quality signal. If we go to the 44 kilohertz sampling rate and 32 bits, we get a much higher fidelity signal. But what does that actually mean? Well, when we convert from an analog to a digital signal, this sort of thing happens. So here's our original signal, and we sample it. So at individual times, we're taking a sample. What is the voltage now? And we store that as a single number in an array of numbers. Then we wait a set amount of time and we sample it again. And we find out what is the level now? Then what is the level now? What is the level now? What is the level now? That gives us discrete points of time where we know what the signal is. However, in between those times, we don't know what the signal is. So we end up with this distortion that happens when we convert from an analog signal to a digital signal. To look at it a little bit more closely, we can see here is our continuous analog signal. We do lots of little samples. And from each of these samples, when we rebuild it, we see we have this step function. And that means that we have this quantification noise in the discrete digital signal that is produced from it. And the higher the number of samples, the closer we can get this digital signal back to its original form. But of course, there are limitations in how close we can go. So what happens if we have a very low sampling rate? Here we have a nice signal, and if we're only sampling it within, say, 2 times per cycle, in this cycle, sorry, 4 times per cycle, you can see that our first sample is here, second sample is here, correlating here, a third sample is here, which is the same point as previously. We're not getting an ideal signal, but we can still recognize it. And as our sampling rate increases and we take more samples, you find that you're starting to rebuild the system back, the signal back to what it originally was, but you will always have some of that quantification error. Now, there's a theorem, Nyquist theorem, that says we have to sample at least twice the highest frequency that's in our signal that we're capturing. So if we want to work with voice, and voice normally works from 300 hertz to 3,400 hertz, we need to sample it around 8,000 times per second. So at least double the highest frequency we want to capture. Okay. So microcontrollers are capable of only detecting the binary signals. So we need to convert those levels, those samples, into binary numbers. So when I said we're putting these numbers into an array, this is the part I'm talking about. So if we look at our sample here at that time, it's reached this voltage, which we equate to 0, 1. All right, anything between this level and this level equates to a 0, 1. On our next sample, the signal has reached this point, which we equate to a 1, 0. When it reaches here, we equate this area as a 1, 1. So this would be stored as a 0, 0, 0, 1, probably a 1, 0, 1, 0, and then 1, 1, 1, 1, 1 after that as an array of numbers. In this case, we have a 2-bit sampling level. So each sample is only 2 bits long. So really not that accurate. And that's what the analog to digital converter does. If we look at our Arduino board, we've got usually an array of analog in, which is the A to D converter. They're a 10-bit ADC, which means we can have 1024 individual levels of the voltage. So quite a fine reading. But again, remember this is a relative level. We will get a level between 0 and 1024, or 1023 to be exact, which relates to a reference voltage. So if we have a 5-volt reference voltage as our input into the Arduino, 512, the halfway mark, will be 2.5 volts. So we always have to remember that we've got to convert back from our number we're storing to our reference voltage so that we get a real reading. This starts to get a little bit complex, but we can go through that as and when needed. An example of what happens when we don't sample often enough, here is our input signal, the blue one. For those who are colorblind, the blue one. And we're sampling at a much lower rate than we require. So we're only sampling at this point, and then at this point, you can see all of the changes that happened here aren't being sampled. So what we would reconstruct is this red signal, which is actually nothing like our original signal, and it's called aliasing because it's similar but not the same. So we've got to be aware that we can't sample too low, and the more we sample, the higher the requirements of the process that we're using. The only other thing I want to quickly mention is filtering, because we usually do this at the very early stages to remove noise. If anyone's used a graphic equalizer, which most people have, that's exactly what filtering is. You're choosing frequencies you want to boost or decrease. The most common one we use is a low pass filter, which means we say we want to get all frequencies from this to this. So in the case of voice, from 300 hertz to 3.6 kilohertz, and we want to throw everything else away because that's outside the normal speech range. So we set up a filter which can be something like this, a simple resistor and capacitor. The bandwidth of the filter is set by the relationship between these two. And as the frequency gets higher, our capacitor becomes much lower in impedance and shorts the signal out. So we get less and less of the high frequency coming through. And that's just a low pass filter. As I said, it's done to reduce the noise we get in many signals. I've got a little example of some gyroscope and accelerometer data. We can see here that our green line is without the noise. Sorry, it's with the noise, and it's choppy and all over the place and jumps around a fair bit. When we do a low pass filter, it takes out this extremes of the signal and reduces the noise component that's contained within the signal. So generally we want to put a low pass filter on any of the sensors we have coming in to limit any of the extraneous noise that gets built into most signals. So what we're going to do now is actually see how we can implement some of this stuff using Tinkercad. But before we do that, just a quick heads up on next week. We'll be looking at IoT networking. We'll be using packet tracer. So please, 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 if you can, download it, install it, make sure you can access it, have a little play around. If you've got time, look at the course that's listed there. It's a little free course, take you 20 minutes to run through, and it gives you the very basic stuff of packet tracer. But Naz will take you through how to set up these devices. Again, it's quite a neat little package. There's one of the exercises setting up a house for security purposes. All the IoT devices are in there. And we'll be able to look at the network traffic, the throughput, many other aspects of the design itself. So we'll now hand over to Savash, who is our expert in Tinkercad, and will get us going on that part.
I might just wait a bit to see if anyone has any questions from the first part.
Yeah.
Feel free to use the raise a hand button or type in the chat or unmute your mics.
Okay. Again, if you've got any questions, feel free to email them to us. If you want further details on some of these aspects for something you might be thinking of building, feel free to contact us. If this was way too much for you, please let me know so that next time round I don't go into quite as much detail or we focus it a bit more. But we would appreciate your feedback on this when you get a chance.
Sorry, got one question.
Yep.
The PWM, you talked about controlling motors and things. Was that more of a signal to tell it how, how fast to operate or whatever, or would that be driving the motor load?
It can be either. Depends on what you've got on the end. So if you've got a motor that's driven by pulse width modulation, then you can control the speed to a certain extent. But generally, it's for the power. So the longer you turn it on, the greater the duty cycle, the more power the motor's getting. Therefore, the more torque it's going to produce and the faster it will spin.
Yep. But it doesn't end up in like a jerky kind of on-off type thing with the motor, or is it just smooth enough that it's
the pulse is usually too quick for that.
Yeah, cool.
You're running it for a few microseconds.
Yeah, gotcha.
Then off for a few microseconds, on for a few microseconds. So when you put it on LED, using a pulse width modulation, you can adjust the brightness, and that's only because of the amount of power that's being dissipated in the LED, but you don't see it flicker at all. Our eyes can't pick that up.
Yeah, and I guess that's if you look at it on the camera, then that's when that picks up that flickering.
Yeah. So, like the props, when you're taking a video of a prop on an aeroplane, it can appear stationary. So you can't get that effect.
Thanks.
Cool. Any other questions before I get to a bit of a play around with Tinkercad? Okay, so I'll start by just showing you some basic stuff you can do in Tinkercad by running through some of the built-in examples, and feel free to jump in anytime. And hopefully by now everyone's registered for Tinkercad. You just need to. It's a free registration. You can use your Google or Facebook accounts, or just sign up using your own email. So hopefully you've done that. So what I'll do, I'll go through some basic examples so you can be familiar with the menu. So basically, when you create your Tinkercad account, right, and you will have, I'll just go to the main page. You'll have a main space here that you can start clicking on new and choosing from a couple of different things. So what I've chosen here is this circuit. So I've created a new circuit. I've just called it playground, and it will be stored for you in your account, so you can go back and add things to it later on. So one of the best things you can do with Tinkercad is let's just go through some of their examples. So through the starter part here, let's go through. How about let's a very basic blink example. So you see, they already have the circuit built for us. So there's the LED, the resistor, and while you're in this mode and you're choosing between different components, you can then click. We can change the color of LED. Look, I like blue, so I'll change it to blue. We have a resistor, so with any sort of sensor actuator that you connect to your microcontroller, you usually have a basic interface between the sensor itself and the microcontroller. So with the resistor, it's very basic. We just want something that limits the amount of current that goes through this resistor, and we can do a very basic circuit calculation. I think Ian showed a couple of examples of it. And then the next step is it will have a cathode and anode. Cathode is a negative pin. We've connected that to the ground. A positive pin connected it to one of our inputs. Then the next step is you can click on this code here, and it will show you the block version. I would suggest use the text version when you're dealing with Arduino. It just makes it a lot easier to go through some of these interactions. And the code that we use for an Arduino is very readable. It uses a lot of built-in libraries. So for example, for simple blinking, all we need to do in this code, we have set up our LED built in, which was connected to our pin 13 over here as an output, then what we're doing is we're doing a digital write high, digital write low with a delay in between, and this is going to cause the LED to blink. So I'm going to start the simulation. So now, and one thing I just noticed this today, that when you actually run the simulation, it plugs in the USB cable, which I think they've recently added, which is pretty cool. So it's blinking now, right? And it's a very simple example, right? So if we wanted to move the switch around, you can run the example code like this, or let's do another example. Let's do one of their, and you can do the typical Control A, Control C, Control V, copying, cutting, and things like that. So I'm going to do
on
the,
that,
sorry, Ian?
I was just going to say on that one,
Yeah.
if you had connected the diode the wrong way around,
Yep.
this
Let's
pole
do that. Yeah,
device, if you swap that around, it won't do anything because
exactly.
it's in the it's not polarized the right way around, and diodes only conduct in one direction. So you've got to be careful that you connect things the right way around where that's necessary.
So if you do it this way, see, nothing's going to happen. And another fun thing that we can do, if we remove the resistor, I think this is because it's just a very small one, it probably wouldn't. You see, so because we haven't put the current limiter, it will give you an error saying, oh, the amount of current that's going through this typical standard LED is too high. So it will it will give you this exclamation mark here telling that, oh, you probably need a limiter here, right?
Whereas in the real world, it just let the smoke out.
Yes. Another interesting example, since we talked about PWM, they have a servo example here. So a servo motor will have an encoder inside, and it only has 3 pins. We have a voltage pin, signal pin, and a ground pin. So this time, with this particular servo, as you can see, again, one of the good things that it has, I'll zoom in a bit here, you can, while you hover your mouse over one of these connections, it will highlight where that wire is connected to. So this particular one is connected directly to the 5 volt V out of our Arduino. And then we have a ground pin connected to the ground, and then a VCC pin or signal pin that's connected here. And you can highlight, you can hover your mouse over the connection, and it will tell you what each of these connections are. So,
Right, so just
yes.
a quick point, just in case anyone doesn't know, a servo is just a motor that you have positional control on.
Mm-hmm. And the way this particular one works, and you can find this for very cheap, like one of the typical actuators that you can get from an Altronics or a J-Car or any typical Arduino kit that you find, you're going to find these types of servos literally blue like this. They'll have the encoder in there, and the way we control them, you're still generating that PWM signal. It's just that based on the duty cycle and the way you're generating that signal, based on that, the encoder will decide how it will affect the direction of the servo, and we can have 360-degree servos, which can be a normal DC motor, and then once you want, and then you will, because you have the encoder in there, you can give it certain directions. So if we take a look at the code itself, so here we are including the servo.h library, and it's telling us that we've attached it to pin 9. So that's the pin 9 that it's attached to. Sorry, this one. And working with the servo, Arduino has a very simple library that has a servo write, and we do a digital servo.write with a position, and we give it a delay. So if I start the simulation of it, you can see the servo rotating in different directions. One thing I'll mention might be a bit too much is if you started looking into things and you started looking into microcontroller programming, you're going to see sometimes that there's sometimes pure C code that we're dealing with when we're interfacing with the microcontroller. And the language we use for Arduino or a typical microcontroller, we call it wiring language. It is still C, but a lot of the setup for interacting with your sensors and actuators would have been done in header files. And so, for example, this servo.h, it has a C library that it will generate a PWM signal based on the pin that we've connected it to. So just if you're interested, just to give you a little bit of detail, what would happen is this particular pin would be 1 bit of a register that's connected to that pin. So we will have to write a particular value into it and then cause a delay. And then that's write a high value, write a low value, and that's what's going to generate our PWM signal. But all of that setup has been done in the library file. So then when we're dealing with it from a pure functional point of view, we just have to call the header file and do digital write and write the do the interaction. So when we usually typically when we have the general functionality of the system done at this level, we would then go and do a in-depth, we'll go one level lower in abstraction, we'll go closer to the hardware and start writing in a C code. It's probably outside the scope of what we want to talk about, which is general IoT, but just something to keep in mind. So, and one of the reasons for that is when you want to write an optimized code, when you want to write that low-level interaction with sensors and actuators, there are parts of your code that you may have to access memory, build interrupts, and kind of disrupt the normal execution and the serial execution of your code. So that's why you just can't do it to this high-level code. And in another way of looking at it, when we're using these header files, we are putting a lot of libraries that we might not be using because when you program the Arduino, it puts some of these header files inside your Arduino. So if we did the same sort of interaction in a low-level C code, the size of the code itself would also be smaller because we're dealing directly with registers. Anyway, so that's, I think, a very good, Tinkercad is free. It's a very good way of interfacing. It's the same type of language that we have with an Arduino. There are a lot of designs that people have done, have made online that we can use and start tinkering with and adding stuff or removing things from it. So let's do a very simple exercise. And here's where I'll ask you to sign in to your Tinkercad account. And I'll share a link with you. Oops. So I'll share a half complete circuit. And what we're going to do, we're going to be adding it into the circuit together and making very small modifications to the code. Okay, so I'll bring up, just share so I can stop sharing so I can share the link in the chat. So please use this link that I've just posted in the chat. It should bring up a window and you should be able to click on, click here to copy and tinker. The circuit. I'll just give everyone a bit of time to just open it up. Okay, getting some thumbs up. I'll share the screen again. This one. So this first circuit, I'll just give it. Hopefully, everyone has access to the Tinkercad. I'll slowly go through it. We're gonna build. I've made some of the connections already, and the code is already given to you. So we're just gonna go through and make some very, very small changes to the circuit. Add a sensor, add 3 LEDs, and based on the temperature, I've put some thresholds here where if we go high, when we're in the middle ground, temperature is going to be green, blue, and red. So let's start adding a couple of LEDs here first. Okay, so and please follow along because that way we can have more of an interactive exercise together. So we can see I've put a 5-volt on this line over here. And by the way, with the breadboards that you have access to, if you hover your mouse over these connections, you can see it will show you how these pins are connected. So for these middle pins, this is how they're connected to each other. for these top rows, they're connected in rows, and for these middle parts, they're collected in columns together. And the reason there's usually a break in the middle of these typical breadboards is if you have integrated ICs, so you can put them in the middle, so their pins won't be connected to each other, so they're middle pins. Okay, so let's add 3 LEDs here. So I'm gonna be putting them okay, let's just move this a bit further down. So one over here, and remember this is my anode, cathode. It's connected to this pin, connected to here, and that's connected to my ground. Let's put one more over here, and one more over here, okay? I'm going to change some of these colors. So let's keep that one as red. Let's keep the middle one so you can click on it and then let's switch the middle one to green and switch this one to blue. Okay, I'll give everyone a bit of time to do the setup. I'll just open up the chat window on my other screen. So sorry if I'm looking to the side. We just in the basic components, LED, we click on it, we'll drag it over, and we place it here where the anode is between this pin, resistor that's going to the pins, and then the cathode is the other one that's going to the negative pins. Okay.
Hey Buzz, were you barking at?
Sorry,
Apologies.
that's okay. Any questions? Everyone's following along, hopefully.
Sorry, do they go as anode or cathode?
So this pin is cathode, and that goes to your negative pin. So if you highlight your mouse over it, and this one is your anode, that's connected to the resistor, connected to these signal wires.
Okay, got it. Yeah.
Okay.
Yep, all good.
Cool. All right. Let's then add a TMP temperature sensor, and I'll place it right over here. And what I've done here, so this pin, this is my power, it's connected to this power line. This pin is my ground. I've connected that to the ground circuit here. And then the middle pin, this is the V out. So one of the typical ways that you'd be interacting with sensors and microcontrollers is there's usually a ground voltage and some sort of a signal pin or a combination of this. And you'd be connecting that signal pin to one of your input outputs of your microcontroller. You might have seen things like you connect this sensor to a GPIO. GPIO is general purpose input output pin. So with a typical, let me show you something. So let's say with an Arduino Uno, one of the things that you'd be typically looking at when you're interfacing with a microcontroller is a pinout map. So if I search for Arduino Uno pinout map, let's just open one of them. This is a good one. What this will tell you is what different pins on your specific microcontroller are capable of, right? So the typical pin, this is a pin out map. So basically you will have, and when you hear the term GPIO, general purpose input output, these are the pins that can have multiple purposes, and they usually can be used for input and output. Now, in this specific case, if I go back to the Tinkercad window, this TMP, and it's a very typical temperature sensor, it's an analog device, so I need to connect it to one of the analog pins of my microcontroller. So in this case, I've connected this to A0, and now our circuit is completed, okay? So the next step is I've left out some very, very basic comments in our code, so you can just see how easy the modification is. So the first thing I've just left out, let's see what pin is connected to our pin. So this is my red LED. So this is the red LED. I know the cathode is connected to the negative pin. So positive pin here. Let's see my red LED highlighted. It's this wire, right? So I'm going to change this value to 8. Then a green LED. So follow that. The circuit is connected to this pin, D12, or you can just put 12 here. And the next one, if I highlight it, and we can use different colored wires. I probably should have done that, but this one is connected. Sorry, we've done red, green, blue. Blue is this one, which is connected to pin 13. So I'm going to change this to 13. So now our code is completed. I've made all the connections, and this A1 pin is connected to this analog part of my temperature sensor. And let's have a quick look at the code. So what have we done here? We have named what each of these pins are supposed to be. So A1 as the temperature sensor, R pin, G pin, B pin as my LEDs. And in my setup, what I'm doing is I'm saying that temperature sensor is an input. I'm setting up the other pins that are connected to my LEDs as output, turning on serial monitor, which you can see here. So if you didn't have an LED connected, for example, in this particular case, we can start printing out something to the serial monitor as well. Then we have a turn off, and we are saying for turning off LEDs, this is my loop. For actually converting the temperature, and this is another good thing to have a look at, TMP, and this is a TMP36. TMP36, the value that we actually read from the sensor, we don't read directly temperature from a temperature sensor. We usually read a change of voltage, change in current, change of resistance, change of some sort of electronic characteristic, and then we look at a data sheet and then convert that to an actual real life value. So in this particular case, what this function is doing over here, it is first we are reading it, then it would go through some sort of calculation to convert that from an actual temperature to from a typical reading to a Fahrenheit or centigrade temperature. So let's run the simulation and see what happens. So the way this is set up, when I'm in this middle part, the green LED is turned on. When I move towards lower temperatures, the blue LED turns on, so it's a cold. And then when I move to the other extreme, I'll turn on the red LED. And as you can see, we can very easily modify some of these aspects. Okay. So any questions so far from this circuit?
Hey, Suvash.
Yes.
I think I missed a part of like getting this temperature gauge, and how did you get it? And
okay, so once
yeah.
so once you click on start simulation,
Yeah.
you can click on the temperature sensor and it will open up this temperature gauge.
Okay.
And this is how you're gonna you can interface, like you can move it, but you can click and hold it, move it around, because this is simulating the change of temperature. Let me just see if
maybe I missed a code something, because it's not temperature thing is not coming up on my screen.
Did you add these pins over here?
Yeah, 8, 12, 13. Yes, I did.
8, 12, 13.
Yeah.
The resistors are this way, and this is a TM. Is it the TMP?
Yeah.
Is that what it says for you?
Yeah.
Okay, you know what I can do? I'll share the completed version, a link to a completed version of this circuit. That should work, so you can have a play around with it, see, and compare it with what you did right now. Let me share the link. This was take a look at, let me just make sure it's shareable. So you can use this link. This is the completed version of the circuit.
I think you're gonna put the USB in as well.
No, once you the circuit I've given you, it should have it will have everything. So
Yeah. So if you start the
yeah,
simulation, then you can change the temperature up and down.
yes. So you
If
have
you
to,
don't
yeah,
have the simulation started, you can't change the temperature.
yes. If you haven't started it, because you start the simulation to be able to modify these attributes. You see, I have found another interesting example at the end was giving the lecture. So it was a light dependent resistor example. Let me see if I can find it again. So light dependent. Okay, found it. So let me share. This is another design. Like a very similar thing, but rather than the LEDs changing based on the temperature, and I'll share the link with you. This is just someone else's design, right? Similar to what I did. I'll just share it in the chat. This particular design, if I start the simulation, it has this. This is a light sensitive resistor. So the way they've implemented this one is when we see the light, so this is after I've started the simulation, it will start the LEDs from turning on. And when there is no light, because this is the way this particular, it's working on light, right? So if it's not detecting any light, it will start doing this basic LED code. So we can already see the way they've implemented it, right? So they've put a threshold, and they're doing setting these as inputs, doing a digital write for the LEDs, putting a delay, and reading it that way. And it's an analog device, so doing a analog read on the resistor itself. Okay, so let's take a look at another quick design together. So this other one, this one is has a couple of other elements in there. So let me share the half complete circuit with you. This is a mini home automation setup. So make sure it's shareable. Yes. Here, copy link. Oh, one of the things Ian suggested me to show you. I'll actually do it here. So if you click on this icon over here, the schematic view, it will show you the schematic view of what you have designed here. And you can download it as a PDF, and can also get a component list for the for the circuit that you would have designed here. So this is the schematic view for the resistor one, and we'll have a very nice look at the design. And this is something, if you ended up looking down the path of designing printed circuit boards for your design, so having a microcontroller and then everything on a nice little printed circuit board design, that's something that you can start using, like use the schematic design that you're doing here. I don't think it's transferable to any of the circuit design applications, but
It is. I think it's just a
is
drawing.
it? Oh,
Yeah.
okay, yeah, it's just a PDF. All right, so let's do the other example. So the one I shared is this one. So we're going to add a couple of fun components into this version. Of my notes here quickly. So let's first put an LED right over here, and let's make sure it's the right orientation. If I'm not mistaken, this is how we can rotate it around. So we can click on the icon and use this to rotate it around to make sure it's on the right orientation. So let's put this right over here. Then let's add a temperature sensor. Everyone managed to get access to this new circuit? Have complete, or did I send it?
I do. Sorry, could you confirm how to do the rotate again, please?
Yep. So you click on the icon on the item, and then you see this rotate icon over here at the top. You can click on that.
Thank you.
Yeah. You can just, I guess you can just click on it and press R as well. That's the shortcut key for it. Then let's add a temperature sensor. And I will rotate this one as well. I just press R, and let's put it here. Another thing we're gonna do, we're gonna add a potentiometer. So let's see, probably under all components. So we were under basic, so I just moved to all components, and a potentiometer. It's just a variable resistor. Let's rotate this one around as well, and put here. And I'm going to add, just wait a bit for people to catch up. And I'm going to add a simple DC motor for this setup. Rotate it. Is it this motor that we have? Yes. So I'm going to rotate it around and use a wire going through here. Zoom in a bit so we can see the connection a bit more clearly. And then use the other terminal going there. Okay. So we put the potentiometer here, rotating it around, temperature sensor here. So same as before, it's connected to A0, put the LED there, and this is the interface circuitry for the DC motor. And the LED itself, it's one of these, there's a bunch of wires for this LED. So I didn't wanted you to kind of just go over wiring everything. With a typical LCD screen like this, usually you can get what we call an I2C backpack for it. What that will do is it will reduce down the number of wires you need to connect that to your microcontroller. So it will look something like this. I2C LCD. A very typical look at it. Let's see if this is the one. Yep. So now with this type of connection, so I2C is just one of the serial communication protocols we can use when we're interfacing with different sensors and actuators with a microcontroller. So the popular ones are I2C and SPI. So I2C and SPI. I2C is a bit more popular. One of the reasons is it has fewer wires. It has a data line, so this SDA line, SCL, that's the clock line, and it will have a ground and a VCC. And then all you need to do is use one of the typical I2C libraries that's available. Now, it's just this example I'm using in Tinkercad. It's just using like a standard LCD. And what that backpack does, it's a small printed circuit board that connects all of those wires to the I2C interface. So then it will spit out the I2C interface for you, and you can connect that directly to the microcontroller. So let's run this code and see how it looks like. So that's the typical simulating it correctly. Is the connection somewhere? Oh, it's because let me use the. Let me share this version of it with you. Might have missed the connection. So I wanted to after this exercise, I just wanted to give you a quick look at the actual Arduino IDE and show your way around that, and you can see how similar it is. So I'm gonna use this thing. Just change some settings so we can take a look at the completed version of the circuit together. Copy. All right, so this link, and I'm going to bring up completed version of it. I think I might have misclicked here somewhere, but I'll share the full version so you can play around with it after the session as well. So what this one does, first of all, there's this potentiometer that controls the brightness of the LCD. So if I move it here, it's going to be blank. Then the way they set this up, it's an automated temperature monitoring system. So when the temperature is okay, everything is okay, right? So if I slightly move the temperature higher, once it checks the temperature, it will see it as being too high, so it will turn on the fan. So it's not perfect, because I just quickly put this together. But then if I go to the other side, start the simulation again, go to the other side. So, and then what about the other extreme? So when it detects the temperature being cold, it will turn on the heater. So it's an automated loop. So if you look at the code here, and I've put where the version of the code is coming from, and you can look it up and look at the documentation that's been provided for it. It's just a bunch of loops that they've set up based on when they're reading the temperature, what happens after the temperature reading has happened, what do we write. And that's how we interact with it. So someone asked in the chat, how do we rotate objects? You need to be outside the simulation environment, so you need to press stop. Then you click on any of these items, either use the tabs right over here, or the shortcut, the keyboard shortcut for it is R, so you can click on it and just press R and it will rotate it around. Let's wrap up this session by just giving you a quick look at like the similarities that this has with the typical Arduino IDE if you haven't played around with it. So I'm gonna bring this up. This is just the latest version of one of the Arduino. It's just a Arduino IDE. So you can see this coding environment is very similar to the way we have the coding over here. So if I go, one of the first things that you can do if you ended up being interested in playing around with microcontrollers and playing around with sensors and these typical interactions, you can go to File. They're basically, the setup for it is very simple. You first have to go to Tools, Board, and you will choose a microcontroller board that you've purchased. So if you have an Arduino, say Arduino Nano board, you'll choose the Arduino from the board manager. You'll choose the Arduino that you have, or let's say I have a Nano 33 BLE. So you'll choose that board. Then under Files, you go to Examples, and there are a lot of very good built-in examples in Arduino's IDE. So one of the best ways that I always, when I'm programming something, and if I see I'm working with a sensor actuator, if I want to make sure that my connections are correct, I'll just run a basic blink example, because this just turns on one of the internal LEDs on and off. And if this setup works, then that I'll know that at least my Arduino connection is correct. So a very similar code, because it's the same language that Tinkercad uses. You choose your board, you click on this upload button, and it will just upload it physically to the Arduino. So if you haven't played around with Arduinos, if you're interested after kind of tinkering with Tinkercad, I think one of the best next steps is going and getting one of these Arduino kits and start like connecting some sensors, connecting some LEDs, and then the next step, which we'll be covering next week, is once you have all this sensor information, you're reading, you're interacting with actuators, how do you then connect this up to a network and transfer information, and what sort of protocols and interactions you can use. So it's a very good tool to start playing around with. Like, it makes it as like Arduino's made things very easy. It has a very you have a very kind of low level of low barrier to entry to just start doing some interaction with sensors and actuators and start kind of getting your feet wet. That's what I wanted to cover for this practical portion. If you have any questions, anything. Sorry, Ian, did you say something?
I'm just sharing my screen. Wait for any questions, but you might be interested to know why you would have different boards. So I've just brought up the Arduino because it's a very solid platform to start using as a beginner. It's probably not the most efficient and certainly not the cheapest ones around, but they are very well supported. So the one we were using in that simulation was this particular Arduino Uno. Now, one of the things you notice is Savash was playing around with the pins sitting out here, and there's a limited number, of course, that you can actually use. So how many switches or sensors or other things can you connect to the device? And the I/O, input output, is one of the limitations. So the Uno is sort of the nice mid-range. We go to the Mega. This has many, many more input output pins. I don't think it's got any processors similar. If you've got lots and lots of input output that you need, then you can move to this. Or if you've got a lot fewer, you can go to, say, the Arduino Micro here, which has physically very much smaller, has a lot less input output devices. You also have the option then of looking at different processors for different power requirements, as in processing power. So if we go to the Potentia here, it's a much more powerful processor, can do a lot more processing here. The Nicola has all the sensors built into it. So we can see just from one supplier, there's a multitude of different microcontrollers that we can choose from. And in the initial stages, you generally pick something a little bit more than you would need, and then you wind back from that. And you try and design something that has the minimum specs, therefore reducing your overall cost, that will still get the job done. As I said, this is just one particular brand. If we have a look at the Raspberry Pi, which is another very common one. There we go. And we look at their These are the single board computers, and they go right from this little tiny Pico, which will run Linux, so a full operating system. You can play games on it. You can run it as a full computer, up to several fairly large capable devices. Oops, that's not what we want. But Raspberry Pi is another good platform to play with.
I'd say I'll just add in this IoT landscape, you're gonna hear a lot about ESP32s. It's a different microcontroller, and the only reason it's very popular is it has an embedded Wi-Fi and Bluetooth connectivity on its development boards. So if you look at kind of typical implementations, similar to a Raspberry Pi, but much cheaper because it's a microcontroller rather than a full-on mini computer. You're going to see a bunch of implementations with ESP32. So that's the reason. And the ESP32 is also, there's also an Arduino core available for it, meaning you can program it with the Arduino IDE. It is not an Arduino. I think it's produced by Espressif. It's the company. Yeah.
But the Arduino has a common platform and it's open source. Lots of people clone them or copy them.
Yeah. And then again, another like just a bit more advanced starting points for Arduino, somewhere between their Potentas, which are dual core and you can do very fancy stuff with it, is their BLE Sense boards. So these they look like a Nano, but they have a Bluetooth Wi-Fi capability built in. So if you wanted something a bit more fun to play around with, that's a good one to look at. But I think if you just go to any of the electronic stores, they're gonna have cheaper versions, like a Funduino or something, for just a couple of bucks that you can purchase and start tinkering with it. And in most cases, it works in similar. They might break up easier, but they're a good starting point, like starting to build small IoT devices for yourself if you're interested in this aspect. Because I've been going through those the first submissions you've had for the IoT course, and a lot of those smart home ideas that you've submitted, a lot of them can be done with a typical microcontroller and a typical Arduino. I think that covers it. In anything else?
Open for discussion. Anyone got any questions, anything they'd like to ask about this, the course, meaning of life, anything at all? Not saying we can actually answer it, but you can certainly ask.
Thank you. Good.
I'll just mention something because it looks like a couple of you've missed the first assessment. Just for your information, we have 3 assessments for this unit. There was the first one, and we can still submit for it. The first 2 assessments, they're good exercises. I've been going through them, providing some feedback. The assessment that will that is mandatory is the last one, so the final assessment, and that's completion of that is attached to you getting the course badge and the completion certificate. But I think it's still good to have a look at completing the first one if you've missed it, because it's a good exercise. It gets you thinking about IoT and designing in IoT. And the next one coming up is about the connectivity of these IoT devices that you would have designed as a part of the first one. So I would recommend having a look at that, and feel free to reach out to us via email between the master classes if there were any questions. Do you wanted some suggestions, feedback for pretty much any general questions you had.
Andrew?
No, I was just going to say thanks again, and see you next week.
Thanks.
As I said, we're very open to feedback. We'd like to know how the course is going, what the master classes, what you think of them, the level, those sort of things. So we don't take offence at all easily. We deal with undergraduate students. All right. Well, if there's nothing else. Oh, hang on. Chris, did you want to say something? I noticed you just unmuted.
I'm just saying thank you.
Nice of you to all come along. It's always worth it when people turn up. Sean.
Sean, go ahead.
Just had a question in regards to, okay, it's interesting, and thank you for the class. In terms of learning how the devices are set up, will there be a class or during the master class about off-the-shelf products with IoT?
We hadn't planned it, no, because, well, nobody asked. But since you do ask, it's kind of hard to do off-the-shelf products because everyone's application is different. It's one of the really interesting parts about the IoT is it's relatively simple to customize what you want to do, as shown with what Savash was doing, taking someone else's design and then just adjusting it so it does exactly what you want to do. You can buy lots of things for, garden automation and looking after pets, lots of home type things. Where it really gets interesting is applying this into business. So counting customers, looking at what customers are browsing within the store, how long they're standing in front of shelves in the retail area. And most of that has to be custom made because each business is slightly different. So it's rather hard to say off the shelf. Off the shelf depends on how you define it.
Sorry,
Thank you.
it's
Yeah.
Andrew here.
So,
I suspect
go ahead,
that David Uono, who's the sort of an IoT person here at Optus, may have some info on solutions that we can offer clients that are somewhat off the shelf, but based on, for instance, people counting technology and things like that. I know we've responded to customer requirements around that using some vendor solutions on that. So maybe if that's something that he can provide some info on. I think he's at some stage during this course he was scheduled to join us.
He is in the final one. What we're planning to do there, and this could be very interesting, is we're going to present a couple of use cases in vehicle monitoring and tracking, and our guide dog one where we turn a dog into an IoT device. And you guys are going to act as the clients who are going to ask us questions how we would implement this. And that will use some off-the-shelf items. Like a lot of the components we're using are very much off the shelf. So for the feedback to the guide dog trainer, we're using an off-the-shelf 360-degree camera. And that's our sensor for that particular part of the application. We're using off-the-shelf temperature sensors to measure the temperature of the dog, inertial measurement units, again, off the shelf for the heart rate, breathing, and, oh, there we go, and the gait. But you then repackage all of these off-the-shelf items to produce the end result that you actually want. You want to talk through that one or at all? We're going to cover.
I was muted. Yeah. So this is actually my wife's PhD research. The idea is we're remotely monitoring the movement of these guide dogs. So this the bottom one is a 360 camera footage that we've just done as a standalone, and the top video is a movement of the guide dog. So the idea is we would be remotely monitoring the way the dog is walking. We'll be monitoring their health attributes, and then at the bottom is the 360 camera detecting objects and obstacles throughout the 360 footage. Then this information would be transmitted to a base station where the trainer would remotely tell the white cane user or the guide dog user where to go, how to turn, where to stop. Because at the moment, if you're not familiar with it, if someone has a vision impairment and they want to go to a new location, whether they have a guide dog or white cane, they have to get someone from the guide dog training center to go with them to that new location, so they can memorize that pathway. And then once they've memorized it, they can go there independently. The idea here is to be able to provide this as a remote solution. So, and especially imagine if someone's in a remote area, right? You have to pay for a trainer to fly there. You have to pay for their accommodation. And while they're there, they can't train anyone else. So with this sort of a setup, using IoT, using in this case 5G for transmission of the data, we are able to provide this as a remote training. So
we're actually with Optus on this particular one because of the reliance on 5G technologies to get the 360 video reported in real time because of the safety issues, but also having multiple data channels. So we've got the data from the dog, which is relatively unimportant on how fast it gets there. It's fairly low bandwidth, but then we've got the voice communication as well, which is sort of sitting in the middle on the requirements field. So we have to slice up the 5G nicely, so that we're getting the quality of service we require for each one of those channels. So for us, it's a really interesting research project, but could be good for the guide dogs as well.
Robert, you had a question?
Yes. So just a question. Can you guys hear me, by the way?
Yes, yes.
Yes. So either the last simulation that you sent through here, the circuit, and I was just playing around with it. So even if you play with the temperature sensor and change it like to really high, it's, I think, did you want us to fix the logic in it as well? Because it says turn on fan, but then the temp is okay and it goes to turn off fan, even though the temperature is high.
Yeah, you can if you want to play around with it. It's just a quick example I found someone else had implemented. But yeah, you're right. The logic for it is wrong because once it detects the temperature, it turns on the fan, but then it doesn't loop back around to check for it again. It just stays in that state.
Yeah, when we get to those control type scenarios, we start to get into a very complex area of engineering control theory. And in these sort of instances, we'd use something called a PID controller, PID, proportional integral differential controller, which allows us not to have that overlap. So if the temperature was sitting right on the borderline, the fan would be turning on and off rapidly. So we want to slowly change things, turn the heater on a lot when it's really cold, and as it approaches the required temperature, you start to lower the amount of heat you're applying. And there's a feedback circuit in there as well. So those were very, very simple algorithms just with a threshold. We don't normally do that in real control situations.
Got it, thanks.
Okay, anyone else have anything to say at all? All right, well, if there's nothing else, we'll wind up. You all have a good evening. We're about to head off home. Being in Perth, we're a couple of hours and 20 years behind you.
See you later.
Thanks so much. See you next week.
Thanks.
Right,
Thank you very much.
Thank you.
Look at it.
Thank you.
Thank you, guys. Yeah.
Okay.